Okay, so I'm checking the microphone. I think you can hear me. Okay, I think it's time to get started. So this is today's plan. So I'm going to finish the OpenMP part by talking about this data sharing thing. And you have some time to work on this OpenMP exercise. And I'm hoping that we can get into this next topic, which is about the GPU programming using CUDA. And yeah, hopefully you have some small amount of time doing this CUDA exercise. So let's get started. Okay, so data sharing clause is our next topic. So in the last week, we discussed how you can use the scheduling clause and some other things to distribute the work. So typically represented by loop iterations distributed across the threads you created in using the hash pragma OMP parallel, right? So how you distribute this work across threads. So this week I'm gonna talking about another important element, which is about data sharing. So in terms of what you have in OpenMP about data sharing is that, so you have parallel for task and these pragmas, and these pragmas actually accept some additional clauses specifying which variables should be shared among threads or between the parent child tasks. So syntactically, it is specified in this section of the OpenMP spec, and you are going to see some keywords like private, first private, shared, and reduction. So I'll get into some of these things. So syntactically, it looks like this. So for example, you have OMP parallel, and in this parallel pragma, you can, for example, specify this variable P is private, and this variable S is shared. So what happens is that actually shared S doesn't do anything significant because this is a default. But just for the sake of clarity, I'm just specifying shared S. So what happens on these two variables is that, okay, so S is shared among all threads created by this parallel pragma. And P isn't. So each thread created in this with this parallel pragma gets its own copy of P. So for example, when a thread assigns some value to P, other threads do not see it. So what actually happens can be simply illustrated as follows. So this printf prints the address of these variables. And the address of S is the same between these two threads, whereas P has different addresses depending on which thread you are executing. So as I said, being a variable to be shared among the threads is the default behavior. So the same thing happens on S if you do not say anything on S. On the other hand, so this seems pretty obvious, I hope, that so if another variable is declared inside this parallel pragma, then the default behavior is actually it's always local to each thread. So there's no way you can share what you assigned to this variable among friends. So the default behavior is a variable defined outside this parallel is shared, whereas a variable defined inside a parallel plasma is going to be private to each friend. So you can change the behavior of variables defined outside parallel by saying this is private or something else I'm going to get into. Okay. So there are some other clauses you can also specify on variables. So shared and private are just what I just talked about. And there are some two other things which might be of interest. Among others, I just omit in this slide. So one is something called fast private, and the other is called reduction. So reduction is actually very important. So I'll get into this later. So the difference between them can be illustrated like this. So when you say, okay, so X is shared, or do not say anything, then so you have only one copy of X, and no matter which thread refers to X, it actually accesses the same location. So what happens is that it is shared. So shared means that so if somebody some threads assign a value to this X and some other threads later read from it, then the second thread is going to get the value written by the first thread. So this is a share. So when you say a variable is private, what actually happens underneath looks like this. So these are named the same. So they are named all the same X. But actually, each of these threads has its own location, so its own copy of X. So when this thread assigns some value to X, it is not visible to anybody else. So first, private is very similar to private, except that each of these copies is initialized by whatever you had at the beginning of the parallel problem. So when you say, okay, so X equals 5 outside the parallel pragma and then enters the parallel pragma, everybody has the same initial value of 5. But afterwards, there's no sharing among these things. So reduction is somewhat more complicated and is going to be very important. So it is similar to private in the sense that each of these threads has its own local variable. So inside this parallel region, there's no communication through this variable. But after this parallel region gets finished, these values are aggregated in some way. So it may be just adding all of these values into a single value, or maybe you can take the minimum or maximum of these values. So it is actually very common pattern in parallel program. So I'll get into this later. So one thing I need to I need to make a remark about before getting into all of this is that so the underlying hardware environment is a shared memory environment. So multi-core environment. For GPU actually is quite similar in the sense that the hardware implements shared memory. So when a core writes some value to a particular address, and some other cores read from the same address, the value gets communicated. So this default behavior determined by the hardware. So it is very natural that behavior of variables in OpenMP are shared by default because this is what naturally happens on this hardware. But at times you need to specify something else. the underlying reason is this notion of a race condition. So when you have a shared memory, the communication or coordination among threads might look very simple. So as one thread writes to some value, some variable, and some other threads read from the same variable, so you can communicate. So it looks very simple in the beginning, but actually it is not as simple as this might suggest. So this is the underlying reason is something called race condition. So first, so what is the definition? What is the race condition? The definition is, okay, so we say that there is a race condition when concurrently running threads access the same location or variable, and one of which writes to it. So when you have a thread writing to a variable x, and another thread concurrently running with that thread trying to read a value, read the same variable, then you have a race condition. So if your program has a race condition, so it almost always implies that your program is not going to work. Because in this, the simplest case I just talked about, so one thread writing to a variable x, another thread trying to read from the same variable. So depending on which comes first, you get a different result, right? So when the reader comes first, then it's going to get a value before the value is written, right? So actually, so the coordination among threads is not as simple as somebody writing to it, some other guys reading from it, right? So this is captured by this definition. So even something as simple as this fragment is not going to work. So what this program fragment is apparently trying to do is, okay, so you initially have x being 1, 2, 3, so 123. And let's say you have 5 threads created by this OMP parallel, and each of them is just trying to increment the same variable x. Then what would you expect x to be here? So if it is always 128, so 123 plus 5, then, well, nothing. There's no issue, but this is not always the case. So here's the simple illustration in which how simple illustration explaining how this can happen. So let's think of what a thread 1 is going to do. So first, it reads about this variable x, and let's say, okay, this is the first guy, so it gets 123. And sometime later, it is, so almost immediately after this, but sometime later, it is going to write 124 to x. So let's consider another thread, just read the same variable x. Right after the thread 1 reads the x, but before the thread 1 writes the updated value to x, then this guy gets the same 123, and sometime later it is going to write 124 too, right? So essentially, one of these updates, so one increment is lost by this sequence, right? So this is well, just one example explaining why this condition is bad, right? So something you need to work on, right? So for this reason, you cannot just say, okay, everything is shared, so somebody write to it and somebody else read from it and you are done. right? So you cannot you cannot be done with that. So there are some other there are some tools to resolve race conditions. So make your program work despite the race conditions. So one approach is something that called make it atomic. So the primary reason why something bad happens is that this update increment is not done atomically. So so while this guy is in the middle of increment, somebody else made something, and yeah, so you somehow obstruct your work, right? So if things always happen like this, so another thread begins reading X only after another thread has done its increment, then you are fine, right? So there are some tools to make some sequence of operation happen atomically. So the particular pragmas the OpenMP has for this is something called pragma OMP atomic and pragma OMP critical. So there's slight difference between the two. I'll get to this shortly. And the other approach, which can be applied only in a limited circumstances, but very useful when it is indeed applicable, is something called a reduction. So all you are doing is actually just aggregate some values partially produced by each of these threads into one value by combining them, just like adding all these values or taking the maximum of all these values. Then there's a special clause for it, so called the reduction. So first about the critical. So the syntactically looks like this. So you say pragma will be critical, and you have a statement. So you can actually have an arbitrary statement, arbitrary C statement, right after critical. The effect is this execution of this statement becomes atomic in the sense that the execution doesn't overlap with some other executions of the other critical state. So this way you can easily guarantee that something like this never happens by just saying ONP critical right before this X++ statement. Okay, this is conceptually very simple, but you should be very careful, not overusing it. So having this critical it is one way you can avoid race conditions altogether. But when you overuse it, the program, so especially when you have so many cores and so many parallelism in the hardware, get quickly very slow. So it doesn't show useful speed up. So avoid this when you can. So another way is something called atomic. It can be considered as a special case of critical. So it can apply to this kind of very limited particular form, like variable equal variable plus something, variable equal variable minus something. So something as simple as this. Then what this atomic statement does is just to guarantee that this read and write, so read and update sequence becomes atomic. So again, this can be applicable to something as simple as X++. So what happens is that Well, exactly, you never have. So it simply guarantees that these two things, so reading X and updating X, are atomic. So nobody else will intervene this single operation. So like I said, the basic effect is just to guarantee that this read update operation is done atomically. So it is not lost. So semantically, it is something similar to this. So you compute this expression outside this critical, and you do this var equal var something plus or something e using critical statement. So semantically, the guarantee you get is exactly the same between these two. But actually, the typical implementations are somewhat different. So if you know something about how these things are handled in the lower level, the critical statement is so general that the only thing you can do is just having a lock and unlock between right before the statement and after the statement. Whereas this atomic statement can be implemented using some special instructions typically supported by recent CPUs. For example, many CPUs have something called a fetch and add operation. So the instruction that does just that. So read, add something, and write the updated value to the same variable, guaranteeing the atomicity. So the atomic should be used where applicable because it is going to be more efficient. So finally, the reduction. It is a very commonly occurring pattern in the parallel programming. And yeah, again, this is something you should use whenever it is applicable. So in general, reduction refers to an operation to combine many values into a single value. Like, okay, you take so many values, V1 from Vn, and you can imagine adding all these values to get the single value. Or you can imagine you take the maximum of all these values. So these operations are commonly called a reduction. So you can call it also aggregation. So reduction is very common in not only parallel programs, so in any sort of program. For example, this is a simple code that is apparently doing some integration. So you calculate f of x on each value in range, and you just multiply it by the increment and compute the sum of all these fx, ftdt, right? So okay, so the computing this f takes some time, so you wanna parallelize this for loop. Then you immediately see that updating this v becomes a race condition, right? So one way you can fix this is to introduce OMP atomic. I just explained. But reduction is something better than this in terms of the efficiency. So in terms of the syntax, OpenMP has something like this. So right after this, not after. So with this OMP parallel pragma, you can say, okay, I'm gonna have a reduction on this variable b using plus. Then what is going to happen is simply that, okay, each of these threads has its own b, has its own local copy of b. So they do not communicate. So there are no race conditions. And after this parallel section is over, partial results computed by these threads will be combined into a single value using plus. Right? So in the parallel section, each thread does its own computation using a local copy of B. And after that, these copies of these are combined into a single value by just adding all these values using plus. So it's very convenient, not only convenient, but also very efficient. So that the primary reason why it's more efficient than other things like atomic is that, so there's no communication between all these threads during the parallel section. So each thread just works on its private variable. Okay, so stick with it whenever it's applicable. That's the main takeaway. So I think I forgot to mention one thing. I don't remember what it was. Okay, so maybe I come to that later. Okay, so what kind of reduction you can actually perform? So there are actually two kinds of reductions. One is something called the built-in reduction. So that is, yeah, as its name suggests, built into the OpenMP language. So you can just check the specification for what kind of built-in reductions are available. But they are just a plus, multiplication, minus, ampersand, something like that. And you can also have minimum and maximum. So these are already useful, especially this plus happens, yeah, so frequently in your program. But built-in reductions are limited to simple types like integers, floating point numbers, and very common operation. So if something is conceptually considered a reduction in the sense that they are just aggregating many values into one, and the order in which these aggregations happen do not matter. But if even if this is the case, if it is not a built-in reduction, you cannot immediately use this reduction clause, right? So the OpenMP has actually a way to define your own reduction for your own data type. Well, in terms of the programming, it's a little bit complicated. So I don't want to spend too much time on this, but just imagine you have this 3D vector class. And what you are doing, so what you're trying to do is to compute the sum of many vectors. So it's conceptually the reduction, right? And you can actually do exactly the same thing like this to do this, right? So just let each thread compute its own partial sum, and you combine them together later. But nevertheless, you cannot just say, okay, I want to combine these vectors using built-in reduction, right? So you can actually define your own reduction using these pragmas. So I don't want to get into this. So you can check the notebook on how to do this and also the specification. But you can actually say, okay, you can name a new reduction, just like plus or min or max, and you can name your reduction arbitrarily, and you specify what kind of type it is supposed to operate on. And you also specify some statement to combine two bytes. Just like, for example, when you are given two integers, you can easily combine this by saying x plus y. So you say something like this here. And in this way, you can define your own reduction. And after you have defined your own reduction, then you can say something like this. So this is the reduction with this BP operator I just defined on variable y, which is of type 3D vector. So you can do something like this. So again, how it works is very similar. So each thread computes its own partial results, and afterwards, these partial results will be combined by whatever you specify by this statement. Right? So this is how you can add a new reduction. And again, reduction is very common in parallel programming. So it's very common and useful. So maybe it's something you wanna. So this slide actually has a final section about how you can do SIMD programming just within the OpenMP spec. But I actually want to get into SIMD programming later during this course, and I don't want to get into it in this OpenMP tutorial section. So this is something you are going to learn in later weeks. So with that, I think I want to finish this OpenMP part. So do you have any question? Okay, so let's have a short amount of time doing the exercise on OpenMP or whatever you need to work on next. So for something like 10 minutes, so until 35, so 5:35. Okay, so we are going to resume in a second. Let me check the microphone again. Checking the microphone. Okay, I think it's working. So okay, let's get started again. So our next topic is GPU programming using CUDA. So it's gonna be interesting. But before getting into this, I got a question about the OpenP. So it was indeed a good question. So the question was, okay, so in this data sharing, I just talked about for reference types like an arrays, we can only use standard model. Is that correct? That was the question. So yeah, you are right. So basically, so precisely speaking, it's not whether it's an array or something else. So it's a whether it's a pointer or not. So for example, when you have, okay, so let me get back to the slide. So the question essentially was, okay, so for example, in this way you can say P is private. But what if the P is a pointer pointing to some data structure like an array? So you can say P, the variable P itself is the private, but you cannot say that the whole elements of the array to be private. So they are still shared, even if the pointer variable itself is made private. So that's basically because the underlying hardware is a shared memory. So you can designate a particular variable that is visible to the compiler to be private, but you cannot say the whole thing is private. So yeah, I guess this is what you're asking. And I think this is a separate question. So is there any log-like mechanism we can use? Yes, there's actually something quite similar to, not just similar. So it's essentially log. Ordinary logging mechanism available in the OpenP2. So I don't get into this in the slide, but I just show the page explaining this. So you can just go OpenP spec and just search for log, and you have something like this. So quite ordinary log data structures and log APIs if you are familiar with those. But basically, a similar thing can be done just by using OMP critical, which is sort of easier to use, right? So the log is nevertheless useful when you, for example, protect this particular data structure using this log, and protect another data structure using another log. This is something you cannot do with just by saying, okay, this is critical, right? So of course you can use logs, and it is sometimes useful and necessary, but I think we're going to talk about it. So thank you for asking. Okay, so let's get into CUDA. Okay. So so the goal of this chapter is to learn CUDA, which is the basic and in a way native API for programming NVIDIA GPU. And for the purpose of this lecture, the parallel programming, I think what I'm going to emphasize is, yeah, in principle, they are just parallel programming after all. So do not be surprised that they are very similar. But so where they are similar and where they are different. So I'll get to this point. If you want to learn more about CUDA by yourself, you can go to this documentation, which is actually quite well written. So I definitely recommend you to take a look when you have time. And there's a book, something called a Professional CUDA C Program, which is sort of detailed, good explanation about how you get, for example, performance. So right after a brief introduction to CUDA, you have some time to work on the exercise. So the first about how to actually compile and run the CUDA program. So the CUDA programs are normally compiled with this NVCC command, so which is also what you have in the Jupyter environment you are having. And conventionally, the CUDA programs have an extension called .cu, standing for CUDA probably. Actually, this NVCC compiler can handle ordinary C or C+ programs too. Otherwise, it looks pretty ordinary. So just say NVCC program.cu. And one thing that is often very convenient is to compile a file having ordinary C or C++ extension like .cc, .cpp, or .c using NVCC compiler as a CUDA program. You can do this by saying -xcu. So that -xcu essentially says, okay, no matter what kind of extension the next file has, it is a CUDA program. So you should compile it as a CUDA program. So this is what this -xcu does. And actually, this is okay. Forget about this one. So in terms of how you run the CUDA program, well, you can just run it by ordinary command line. So this one was written for submitting a job in a supercomputer environment, and you can just say /a.r without this run thing in the Jupyter environment you're having. So you can learn all these things in the Jupyter notebook too. So let me get started about how you actually write the CUDA programs. So before getting into programming aspect, just have some understanding about what the GPU looks like as a device. So the very first thing you have to keep in mind is GPU is a separate device. It is a device separate from CPU. And as such, code or functions that are supposed to run on GPU must be so designated. So you have to say, okay, this is a piece of code you want to run on GPU, which makes programming somewhat more tedious than just ordinary OpenMP programs. But this is the way it is, at least for now. It is also, so the other thing is that data also must be moved between CPU and GPU back and forth, because these are two separate devices. So there's no automatic data sharing between CPU and GPU. But it is actually changing these days. So many GPU vendors, including NVIDIA, AMD, and also Intel to some extent, trying to more tightly integrate these two computing devices, where it is simply stated, it's a shared memory between CPU and GPUs. But for the time being, you need to assume things look like this, and you need to move data between CPU and GPU when necessary. And somehow a GPU is in this context often called a device. So when you hear device in the context of GPU programming, it is actually meaning GPU. And a CPU is often called a host. So instead of saying CPU and GPU, we often say host and device. So that's one some of the terminologies you want to remember. So the very basic thing when you actually start programming GPU or CUDA most specifically, these two things. So the two things you need to learn before anything else. Just like there are two things you need to learn before anything else in OMP programming. It was OMP parallel and OMP4. So in the case of CUDA programming or GPU programming, the first thing you need to learn is this concept of GPU kernel, which is often simply called a kernel. It is a function that is supposed to run on GPU. And in terms of the what it looks like in your program, syntactically it is just an ordinary C++ function whose return type is void. And you have this magical __ global __ keyword in front of the function. So this is the hallmark of GPU kernel, and something that is supposed to run on GPU. And once you have this GPU kernel, a function that is supposed to run on GPU, you can launch that kernel, specifying the number of threads using this awkward syntax. So F3, so triple less than two numbers followed by triple greater than. This is a peculiar and awkward syntax to launch many threads on GPU device. So the effect of this kernel launching code is to create NB multiplied by BS number of what is called CUDA threads. Each of them is going to execute this kernel function. So this can be illustrated like this. So I'll get to these terminologies like thread blocks later. But so what this picture is trying to illustrate is, okay, so you have this NB number of group of threads called thread blocks. And each of these thread blocks has this BS number of threads. So in total, you have NB multiplied by BS CUDA threads. So you can legitimately wonder why you need to specify two numbers separately. So what is the point of separating the number of threads into two factors, right? So it is quite a legitimate question. So I'll come to this point later. But for now, just this is just an NVIDIA way of specifying the number of threads. So launching a kernel like FNBDS, in terms of the semantics, looks like executing the following loop in parallel. So you have a for loop executing NB multiplied by NB multiplied by BS times. Each iteration of which is doing this F, right? So you execute F this number of times, but all concurrently using so many CUDA threads. So semantically, yeah, it is like a parallel for loop, right? Except this awkward kernel launching syntax. So here's a simplest example. But simplest example is already somewhat complicated. So this example is trying to launch so many threads, each printing some hello world type message, having its ID and the total number of threads. So I'll get to these variables later, but this is the CUDA way of knowing the rank, so your rank in the team of threads. And this is the CUDA way of knowing how many threads are actually launched. So these, yeah, some built-in variables CUDA defines. And yeah, all these variables may already make you somewhat scared, but yeah, this is yeah, what the CUDA is. So what you have is once you define this kernel function, you launch this kernel function CUDA thread fun. You just define here some specified number of with some specified number of threads. So let's imagine you wanna do this with n threads. So you originally have this n. So let's imagine it's 1,000, and you divide it into a number of thread blocks, and you have to specify the how many threads you have in each what is called thread block. You also specify the number of thread blocks you want to have. So instead of just saying I want to make 1,000 threads, you need to say two separate numbers. And let's say you want to have 64 threads within each thread block. Then you simply calculate the number of thread blocks you need to create by basically dividing n by 64. But just to make sure that you don't forget the reminder when the n is not divisible by 64. Make sure that you add 63 and then divide it by 64. So by having this number of thread blocks and this number of threads within each block, yeah, you make sure that you create at least 1,000 threads. But as you can easily notice, you actually end up creating slightly more than 1,000 threads because 1,000 is not divisible by 64, right? So in this particular case, you end up creating 1,024 threads, right? 64 by, what is it? 16, I guess. So this is the reason why you have to have something like this. Okay, so sorry. This is a typo. This n thread should be n. So you pass this 1,000 as a function parameter, and each thread calculates its own rank. So you get a number between 0 to 1,023. So 1,024 minus 1. And you make sure that if your number is larger than equal to or larger than 1,000, you don't do anything. So this is the reason why you have to have something like this, which is very typical in CUDA programming. So you cannot create exactly the number of threads you want. So you create threads slightly more than what you exactly need. And inside a kernel, you do something like this. Okay. And then you have a program that prints a hello exactly n times, right? So this is simplest example you have in CUDA. Okay, so I got a question. So why is it divided into blocks? What would be the difference if we have one block with 10 threads or 5 blocks? Yes, this is indeed a good question. And this is exactly the thing I'm going to get into when you talk about how this actually works and what is happening underneath. And the short answer for now is it affects performance very much. So how many threads you have in each block. So how you organize the whole threads you need affects performance. I'll get to that later, but I cannot get to that just now. So it's a very important question. I cover later. So yeah, this is it looks very peculiar and somewhat awkward, but this is a good way of launching so many threads and doing so many things in parallel. And you are creating something called CUDA thread by doing this. And it is, so if you of course remember OpenMP also has the notion of threads, which is something you create by having OMP parallel, right? But CUDA thread and OpenMP thread are the similarly named, but they are very actually different. So how is it different? So in the shortest term, so launching something like 10,000 or even 100,000 CUDA threads is indeed a quite common programming idiom you have in CUDA threads. So you are not surprised at all by looking at something like this. So you create something like 256,000 threads, all doing this function F. So when you compare this to OpenMP, so launching even 10,000 threads, let alone 1,000 threads, let alone 10,000 threads on CPU using OpenMP using this OMP parallel is almost always a bad idea. Even if they are semantically in a way very similar and almost identical. So when you have, for example, plasma OMP parallel followed by the function for F, I'm saying, okay, you have this to 556,000 OpenMP threads. Semantically, it is very similar to what you have here, creating the same number of CUDA threads. But what actually happens underneath is very different. So it is very common to do something like this, but doing something like this is almost a bad idea. Never do this. So the same thing can happen. The same thing can be done in OpenMP much more efficiently by doing something like this. You have a loop that iterates this number of times, and each iteration doing F. So and run this program using a much more modest number of threads in the command line. then what happens is that you create something like, for example, 50 threads, 64 threads, whatever number is reasonable on that platform. And these 50 or 64 threads will divide these number of iterations among themselves. So this is the OpenMP way of doing things. And this is CUDA way of doing things. Okay. So the primary reason why this is the case is that so OpenMP thread is essentially an operating system level thread. And typically multi-core processor has only so many cores. And each core can run at least at most a couple of threads at the same time by the hardware. So you have so much more threads than the actual number of cores. These so many threads need to interleave by the operating system. So by operating system intervening each of threads from time to time and switch between these threads by using software. It is not efficient, and moreover, it is never efficient than just having only a couple of threads at each core. So that's the primary reason why you almost never want to do something like this. But CUDA is different. GPU is different. So I got another question. Should you always work with power? No. So the number of thread blocks and the number of threads in each thread block is arbitrary. So it doesn't have to be a power tree. So one thing, so one small thing is that so when you call a kernel doing something like this, the execution of this kernel and whatever follows this kernel call on the CPU side happen at the same time concurrently. So the kernel call and the host code and following the kernel call will overlap. But it does not mean two kernels execute at the same time, even if you call another kernel right after this. So what happens in this particular example is that G and H1 will happen concurrently. Just so that primarily because the GPUs and CPUs will not communicate by default. They do not share memory. So doing these things in parallel do not affect the semantics almost at all. So there's no reason why the CPU waits for this kernel code to finish by at least as a matter of default behavior. But if you subsequently call another kernel, this kernel launch should wait for the prior kernel execution to finish. So this is exactly what happens by default. So it is sometimes important when you measure the performance of computation. Basically, it often happens that you want to measure the time particular kernel call takes in your program. But if you look at the clock right before the kernel call and right after the kernel call, it does not reflect the time this particular kernel call actually took, right? Because the CPU immediately continues the execution right after it launches the kernel. It doesn't wait for the completion of the kernel by default. So you have this CUDA device synchronized method to make sure that the CPU side does not go further until all the kernel calls finished. So especially when you measure the time of a particular kernel, you have to remember this API and make sure that you look at the clock only after you make sure that the kernel code gets finished. So this is yes small but sometimes important. And yeah, I get to this thing I have just shown in this the first example. What are all these block dim, block index, thread index, and grid dim on these things? So this is something similar to what you had in OpenMP by two API calls. One was OMP get num thread, and the other was OMP get thread num. So the first one tells you how many threads are executing the same parallel region, parallel section you are in. And the second one, OMP get thread num is the rank or the position or your ID in the number of threads you have. So these variables, built-in variables, give you something analogous to this in the context of CUDA program. So again, the primary reason why you want to do this is, well, whenever you do something useful using so many threads, each thread is almost always want to know, which thread you are, right? So in the team of threads you are working together. So you get it from these built-in variables. So remember that when you launch a kernel, you say something like this, right? And like I said, you specify the number of thread blocks. So the number of boxes in this particular figure. And the number of threads in each thread block or in each box in this figure. So these two variables called block dim, grid dim, give you how many threads. I'm so sorry. So first of all, this grid dim gives you how many blocks you have in total. So grid dim was more specifically grid dim dot x. The field x of this variable is the number you specified as the number of thread blocks you want to get. And block dim gives you the dimension of the size of each block. That's why it is called block. Right? So specifically block dim dot x is the number of threads in each block. So dim means dimension, the size. So one thing I just want to tell you, just to make it easy to understand the whole thing. So in CUDA programming, you call the entire thing grid. So this entire thing is called grid. And each box is called a thread block or just simply block. And what you have in each block is many threads. Right? So you have block dim and grid dim. And there are two variables that tell you the position in your position in the entire grid and in your block, right? So thread index, or to be more precise, thread index dot x gives you the ID within your block. So it is a number from 0 to block size -1. And block index gives you which block you are in the entire grid. So it's called the block index. So by having these two numbers, you can calculate the ID, your ID in the entire space. Let me get back to the example. So this is what it did. It was doing, right? So this I gives you the the the, the global ID, so for global ID in the entire grid. So the whole thread. So it multiplies my block ID by the size of each block. So this number gives you the number of threads and that are in thread all the thread blocks before myself, right? And you add my thread ID within my block, right? So this is how you get the global unique number within the entire number of threads, right? And to make things slightly more complicated, slightly more flexible, I should say, well, actually, each of these dimensions, block size and grid size, can be up to 3D numbers. So each one takes up to 3 numbers. So when you simply say, okay, so this is the number of blocks you want to have and number of threads you want to have. Yeah, you essentially specifying the 1D block and 1D grid. But you can actually say, okay, so you want to have threads within a single block arranged in 8 by 32 ways. So instead of just saying 256 threads. So in terms of what happens in the hardware, these two are almost identical. So you end up creating 256 threads after all. But for the sake of your convenience, especially when you, for example, are working on two-dimensional arrays, you may find something like this useful. And you can also have two-dimensional number of blocks, and you can also have three-dimensional way of specifying block size and number of blocks. So just use it when you find them convenient. So it doesn't affect the performance very much, in my understanding. So yeah, this is how our learning example of sparse matrix vector multiply could be written in CUDA. So we are assuming here that so-called CU format, coordinate list format. The whose original serial code looks like this. So it is simply a one-dimensional loop iterating over all the non-zero elements of the matrix. Right? And you get pitch low, this non-zero element is in, and pitch column, this non-zero element is in, and you do this, something like this. So the basic way of parallelizing a loop like this using CUDA is, well, so it may not necessarily be that simple, but the most simplistically, you simply write a kernel function that executes a single iteration of this loop, which would look like this. So you do this in a function, right? So a single iteration of this loop. And you just make sure that you are not surplus threads, which are outside this number of non-zero elements. So just like we did in the first example we have witnessed, right? So in this way, yeah, it's pretty easy to parallelize a simple loop like this. And you launch this kernel, doing a work for a single iteration by creating, whatever necessary number of threads. So in this particular case, let's say you decide to have 256 threads in each block, then you similarly calculate the number of thread blocks you need. And you specify the number of blocks and block size this way. And inside the kernel, you want to make sure that the threads that are not supposed to do anything will not, in fact, not do anything. And actually, we are not done yet. So for the same reason that this coup format cannot be easily parallelized using a parallel for loop, just as we witnessed in the OpenP2. The reason is that, okay, so using this kernel, many threads working on each of these non-zero elements, there may be a situation in which two or more threads are trying to update the same element of Y, right? So this needs to be resolved in some way, just as we discussed today in the context of OpenP. But principle is exactly the same. So no matter whether it's CUDA or OpenP, no matter whether it's GPU or CPU, as long as two concurrently running threads are trying to update the same variable, something needs to be done. And what I don't know why I started talking about this now. Oops, maybe I am somehow skipping like, I don't know. I come back to this later. But, so how you resolve a situation like this in CUDA program? I'll get to that later. Something else I should talk about, but there's so many things I should talk about. I guess it's good to have another time you can work on the Jupyter notebook. So you should have CUDA's P02 CUDA, and actually another one trying to show how CUDA actually works using the visualization. But just let's just have a time to do some experiment using CUDA. So you should have this one. So PD02 CUDA. So another 10 minutes or something. So right before today's lecture is going to end. I got a question. So if the GPU flip now is bigger than the physical CUDA core now, how will it schedule the load? Okay, so that's another good question. So actually, so you can have many more threads than the actual number of CUDA cores or streaming multiprocessor in NVIDIA terminology. The GPU can still handle it. So this is by having a scheduler dispatching thread blocks to available streaming multiprocessor. So I'll get to that later. And So you want to know how to handle race conditions. So yeah, so the reason why I didn't get into that is simply some credit that I thought I was supposed to be there was missing. So I checked the slide again and yeah, to talk about it. But in the shortest time, shortest answer is the shortest answer for you have something like atomic into the API, so you can use it. Yeah. So just to continue answer to your question, so it looks like I thought I rather talk about it in this separate section. So if you are interested, then you can just go and look into this section. Yeah. Okay, so I forgot to mention one thing. So for this CUDA exercise, you need to access a separate post, which is described in Jupyter Notebook itself, but it may not have been entirely clear. Right. So you actually need to access this URL. So tablex000 zap.org followed by colon 8000. So this is the URL you should access. So don't forget this column 8000. Well, I don't know what you mean by right now you are using this URL with host name tablet. You should be able to access this URL like this. So does anyone have trouble accessing it? Okay, so it may not be visible to everybody in the room. So the URL you need to access for the CUDA experiment is Yes. Okay, okay. So have length. So G stands for GPU. Yes. What kind of data? Can you show your screen? Okay, so the same issue. So I like to see what it exactly looks like. So anyone, you can share the screen. Sure. Oh, okay. Maybe the server is somehow dead. I just was able to access some of this thing. I don't know. I'm somehow able to access this. Let me check. Um, the question can, okay. Could it be because the other tab is open? I don't think so. It shouldn't matter. Already? So if you close the other server, then it was fine. Well, actually, no, but they are on the chat. It says close the other server and somehow you are able to access the other one. Did you do that? Okay, okay. So you close the other server. Okay. So I don't know why, but yeah. So what you have in the chat is in the way you can work around the problem. So the close the other server. So because it doesn't happen to me, I don't know what kind of problems happen in other eyes. Okay, so there's another suggestion that if you shut down the other kernel, then it's fine. Okay, so okay, logging out from the other server. So all the tricks are pointing to the same direction. So you don't want to mess up with two servers. Just separate them. So maybe the last result is to open a private window or another window having a different profile. Maybe the last result. Thank you for helping each other. That's a good thing about the report class. Okay, so I think it's time to finish the class for today. So if you don't have any question, I'll get finished right away. Okay, so okay, let's finish it for today. Thank you.